Good morning. This is Professor David J. De Los Reyes. I will now be having what you call this, a lecture for this morning. This will now be lesson number 10. This is advanced mathematics. We are now on lesson number 10. So I will be discussing for this morning it will be application problems of the so-called non-homogeneous differential equation. Application problems. And this is applied to electrical transients. Okay, let's proceed. I will check my camera if it's working or not. Oh, it's fine. Our lesson for this morning will be advanced math. Lesson, this is now number 10. Okay. The topic is application. This is on electrical transients, and for this morning I will be discussing the solution of a, what they call this, RLDC circuit. The meaning of RL is that the component of the circuit is a combination of a resistance and an inductance. Inductance is a coil, okay? And it is being energized by a direct current, meaning it's energized by a battery. So this is resistance and inductance in series, energized by direct current DC. This is the battery. So actually, if we try to figure out our topic for tonight, this will be the figure. We got a battery here. This is the complete circuit. The first component of the circuit is a resistor, and the second component is a coil or inductor. And we got a switch here, and the circulating current. If we try to close the switch, there will be a circulating current. It's a closed circuit now, so that circulating current is designated by I. And the problem is asking for I as a function of time. The given initial condition is at time t equal to 0, the current is 0. Meaning, after closing the switch, initially the current is 0. That's the initial condition. That's why I place it here at time t equal to 0. I is equal to 0. So what will be I as a function of time? Oh, this is now a very interesting problem because we now know how to solve a non-homogeneous differential equation, and we are on the application problem. So actually, this is a little bit interesting. Why? We should derive the equation by using our knowledge of the so-called solution of a non-homogeneous differential equation. I will check again my camera. Okay, let's proceed. We are given the circuit. This is what is required. Let's try to bring out the solution. By using our knowledge of differential equation, and this differential equation falls under advanced mathematics. Okay, it falls under advanced mathematics because what is it? The right hand side is not equal to 0. So okay, I will place the solution here. Sigma notation. This is capital letter B. The meaning of this is that in electrical circuitry, we read this as simply summation of the voltages around the closed loop. Okay, that's the meaning of this. The sigma notation, then capital letter B, meaning the summation of the voltages around the closed loop. Okay, so to bring out the required differential equation that will lead us to the solution of I as a function of time, we will start with this. That is, we will take the summation of voltages in D should be equal to 0. Okay? Voltage drops is minus, voltage plus, voltage sources is actually a plus. So if we try to take the summation of the voltages here, this is negative positive, that will be plus E. okay, minus the drop over here, the voltage drop over here. And this is designated by B sub R, this B sub R. Minus the voltage here. This is a coil or inductor. And the voltage across it is designated by B sub L. This is a drop, this is a drop, and this is a voltage source. So this is plus E minus BR minus BL, okay? And this should be equal to 0. That is after closing the switch. It should be a closed loop, because if it's not a closed loop, we could not do this one. It should not be equal to 0. Okay? So substituting values now. A plus E, under DC circuit, the voltage across a resistor is just the current passing to that resistor times the value of the resistance. So this is actually IR. And for a coil, B sub L, this is a changing voltage. If you try to recall one of your formulas under physics, the voltage across a coil is actually designated by di over dt times L. This came from physics. Okay? Whether we like it or not, the voltage across the coil is actually changing at any moment in time. It is changing. It is actually di dt times L times the value of the inductor. This is as a function of time. Whether we like it or not, it should change with respect to time. That's why B sub L is actually di over dt times L. So this is the second part of the negative one now. Negative BL now will be L times di dt, and this should be equal to 0. Neglecting the resistance of the connecting wire. Because if there is a resistance of the connecting wire, okay, that's another thing. We will add up more on the value of R over here. For the meantime, the resistance of the connecting wire is 0. So there is no more I times small r maybe, where small r refers to the resistance of the connecting wire. For the meantime, small letter r is equal to 0. So the equation is just a simple one. E minus IR minus L di dt, and this should be equal to 0. If we try to rearrange this equation here, we'll transpose this two here to the right rather. Then we try to rearrange. Okay, this will now be L di dt plus IR, and this should be equal to E. And multiplying all the terms by 1 over L. Okay, we would like to eliminate this L here. So L di dt times 1 over L, this L here cancel with this. First part will just be simply di dt. Okay, IR times 1 over L will be, I will make the ratio R over L as 1, okay, because we will divide this by L if we try to multiply this one, right? So I can write this one as simply R over L times I, and this should be equal to, the right hand side should be E times 1 over L is actually E over L. And if you try to notice it, okay, there is something like similar to this equation here. Okay, it's a so-called differential equation. Instead of x and y, it will now be current as a function of time. So actually, what is given now is first order non-homogeneous differential equation. Why first order? Di dt is first derivative, right? And I is just simply I. And this is equal to E over L. Since the right hand side is not equal to 0, this is non-homogeneous differential equation. And this is actually an application of our topics from number 1 to number 9. Because we are now on lesson number 10. That's why I give you the concepts on how to bring out the solution. I give you example problems of the different variations in the problem. And for tonight, we are now applying those concepts. Okay, let's try to bring out the solution of this. To compute for I as a function of time, the right-hand side is not equal to 0, so supposed to be the total solution will be complementary plus particular. Right? We know how to compute for the complementary solution, right? Okay, let's proceed. I sub C, meaning complementary current, this should be equal to K e raised to MC. Actually, what we are doing from the previous discussions, this is Y, right? For the meantime, replace that Y by I, okay? It's the same. If we try to take the first derivative of this complementary solution with respect to time, the I complementary with respect to time, this should be equal to, it's a constant times exponential function, so it should be K times e to the mt times the derivative of exponent, which is m times 1, or just simply km to the mt. Okay? Substituting km a to the mt, that's the first derivative, okay, plus the ratio r over l times the value of I complementary, it is k e to the mt. And for the meantime, while we are taking the solution complementary, we will equate the right hand side to 0, so this is equal to 0. Then if we try to multiply all the terms by 1 over k e raised to mt, right? This k here cancel with this, and this e to the mt cancel with this. What remains on the first part will just be simply m. For the second one, this k here cancel with this e to the mt cancel with this. Second part on the left hand side will just be simply the ratio r over r, and for the right hand side is 0 times 1 over k e raised to mt is still 0. So this is 0. For the meantime, the resulting characteristic equation is not quadratic, it's linear. No problem with that one. It's easier to solve a linear than a quadratic, right? So we are now given a linear equation involving m and the ratio resistance and inductance of the resistor in coil. So if we try to equate this one to 0, m1 now will be the ratio negative r over l. I will check my camera. Okay. Therefore, the complementary solution now, we now know the value of m1, right? So we'll go back here. We'll place I sub c now will be, okay, there will be another constant later on. So I will now try to place the proper subscript here. It should be k1 a raised to m1 minus r over l times time. And this is the complementary solution. Complementary solution is actually the transient part of the current. Transient part. Why transient? Because it involves time. Okay? While time is changing, the value of the complementary current is changing. That's why we call this the transient part. The complementary solution is the transient part. Transient. That's why our topic tonight is transient. It involves time. Okay, let's try to bring out the particular solution. For the particular solution, I will place here try I particular should be equal to K2. Why K2? K2 is a constant, supposed to be, right? Why I assume that the particular solution is just simply K2? Because if you try to notice it, the resulting first order non-homogeneous differential equation, the ratio E over L, it's just constant. Okay? E is constant, the inductance of the coil is constant, so a constant over a constant will still be constant. So if we try to bring out the particular solution of this, it will still be constant. Okay? So we try I particular should be equal to K2 taking the first derivative of the particular assumed solution. di particular with respect to time, and this should be equal to the K2 is constant, so the derivative of a constant with respect to time is 0, so this is 0. Okay, substituting, where I will go back here, we'll place this value here. So what will come out? Di over dt is 0. Okay, plus the ratio R over L. Okay, times I particular is K2, right? This is K2. And this should be equal to the right hand side. We are now solving for the particular solution, so we will take the value of the right hand side. Okay, it should be the ratio E over L. This is now 0. Okay, I remove the plus, I will multiply all the terms by, there is a common term for both the left and right. So to eliminate that one, we will multiply all the terms by, okay, it should be the reciprocal of 1 over L, so we will multiply all the terms by L. So the left hand side multiplied by L, this L here, cancel with this. Okay, the right hand side multiplied by L, this L here, cancel with this. So if you try to notice it, it will just be simply R times K2, and this should be equal to E. And solving for K2, we will try to eliminate R, right? So we divide this by R, we divide this by R, this R here cancels, so K2 is simply the ratio E over R. This is. Okay? So the particular solution will be the ratio. We'll go back here, we substitute the computed value of K2. I particular now should be the ratio E over R. And this is now actually the particular solution, or the so-called steady state. Steady state current. Steady state meaning the value of the particular solution is not affected by time. At any moment in time, the value of the particular solution for RLDC will just be simply the ratio E over R. But for the complementary, as you notice it is in terms of time, right? So as time changes, this complementary solution is actually, since this is negative, okay, as time increases, this will be a big value, but since it's negative, this is approaching the value 0 actually. Because I complementary will just exist for a very short period of time. Okay, to bring out the general solution now, the total general solution will be the complementary solution plus the particular. Okay, that's our concepts from lesson number 1 to number 9. It should be complementary solution is K1 A raised to minus R over L times time plus the computed value of the particular, which is E over R. And to compute for I as a function of time, because for the meantime K1 is unknown. So we will try to bring out the initial condition that at time t equal to 0, the current is 0. Just after closing the switch, the current is 0. It will start from 0, okay? So I place it here at time t equal to 0, current is equal to 0. Substituting values, 0 should be equal to K1. If time t is 0, the ratio R over L times 0 will be 0, and E to the 0 is 1, so this is times 1, plus E over R. K1 now will be a negative E over R. We will place this on the left to solve for K1. So this unknown value of K1 is actually negative E over R. Okay? So the total current solution now will just be simply, what's that? There is a common factor E over R, right? And this Q1 here is negative E over R. So I will put this one ahead, then I'll try to factor out. What will come out for the total current as a function of time will be the ratio E over R times the quantity, 1 minus E raised to minus R over L times time plus quantity. This is now I as a function of time. So at any moment in time, okay, just specify the time, you could compute for the current. Okay, and the graph of this is something like this. The ordinate will be the current and the abscissa will be time. This is a horizontal asymptote. And the equation of the horizontal asymptote is I is equal to E over R. This horizontal dotted line, horizontal asymptote. And the curve is actually this one. It emanates from the origin, then it goes like this. Then as time passes by, okay, this is approaching the horizontal asymptote. So you could actually see that the transient current only exists maybe up to this time here. Because after maybe 1 hour, the total current now is actually just simply E over R, because the ratio or the value E raised to minus R over T is actually approaching 0. Oh, that's the graph. Okay guys, that's the application of the so-called differential equation, which is non-homogeneous, and for tonight it is a first order non-homogeneous differential equation. I will check my camera again. Oh, that's it. That's the importance of the so-called advanced mathematics under the lesson non-homogeneous differential equation. It is actually a solution for problems involving circuitry. And our circuit for tonight is a combination of a resistance and inductance connected in series, energized by a direct current voltage. So the current as a function of time for RL DC is actually the ratio E over R times the quantity 1 minus E raised to minus R over L times time. Okay, that's the solution. Try to take note of this equation here, because later on, under the topic, still under advanced mathematics, if we try to go Laplace transform, we will derive again this formula by using Laplace transform, because our solution for tonight is differential equation. And one of the topics, important topics under advanced mathematics is actually Laplace transform. Okay guys, that's it. If you like my video, please click like. And if you want to subscribe to my channel under the so-called topic advanced mathematics, okay? I got 4 topics already, which are long-form videos, differential calculus, integral, differential equation, and this is now advanced math. This is the 4th topic which involve long videos, okay? The syllabus for this is complete, okay? So if you would like to subscribe to my channel is at youtube.com/@prof.davidj.de. And if you want to share it, please click share. Good morning, Los Angeles.